In this video, we're going to look at a way of calculating the probability of two events happening, A and B, if they are dependent on each other, not independent. So you should already know that if A and B are independent, then the probability of A and B is just the probability of A multiplied by the probability of B. Well, the problem is we want a formula that works out the probability of A and B happening if they are dependent, if they're not independent. So let's have a look at that. So not independent. Well, unfortunately, it's not going to be as simple as just timesing the two probabilities together. Well, in order to derive this formula, we're going to start with the probability of A given B. And we know this formula from conditional probability is the probability of A and B happening divided by the probability of B happening. So if two events are not independent, we can rearrange this to get the probability of A and B happening. If you times both sides by probability of B happening, we're going to get probability of B happening multiplied by the probability of A happening given B has happened. And this is a really useful formula, and it can tell us what's the probability of two non-independent events happening at the same time. And if you want to try and get an intuitive understanding of where this formula comes from, it might help to think about a tree diagram. So on this tree diagram, I'm going to put the event B happens and the event B doesn't happen. And if B happens, then either A could happen or A doesn't happen. And similarly, if B doesn't happen, A could happen or A doesn't happen. So what we want is we want a formula for the probability of A and B happening. So we want to work out what's this probability here, because that probability there is going to be the probability of A and B happening. Well, for the probability of B, I'm just going to write that as probability of B. And we've got to work out what goes on these branches. So if A and B were independent, then it wouldn't matter whether I've gone along this B branch or along this not B branch. The probability of A would just be the probability of A. But if A and B are not independent, then that means that this probability is going to be different to this probability. So here I actually need to put the probability of A, given that we've gone down this B branch, given that we know B has happened on this branch. And similarly here, I would have to put the probability of A not happening, given that we've gone down this B branch, given that B has happened. So in order to work out this probability here, we times along the tree, along the branches of the tree diagram. So we're going to do probability of B multiplied by the probability of A given B. And that's an intuitive kind of understanding of where that formula comes from. So let's have a look at example 7. We've got two events and we're going to assume that they're not independent because we always do that with events. And we're given this formula here. Now, it's going to be useful to write down this formula in terms of what it's actually equal to using the conditional probability formula. So that's the probability of C and D divided by the probability of D. And we're told that that's equal to 0.3. Well, in part A, you might be tempted just to say, well, I know the probability of C and D happening. That's just the probability of C times by the probability of D. The problem is, we're just told that it's two events. We don't know that they're independent. So we can't just times their probabilities together. Instead, we're going to have to rearrange this formula to get C and D the subject. So the probability of C and D happening times both sides by the probability of D. So we're going to get 0.3 times by the probability of D. And we're told the probability of D happening is 0.6. So we're going to do 0.3 times 0.6 to get 0.18. And another way of doing that, we could have just used the formula. The probability of C and D happening is the probability of D happening multiplied by the probability of C happening given that D has happened. And we would have got the same answer, 0.18. Let's have a look at part B then. So in part B, we want the probability of D given C. So let's write down what that formula is using the conditional probability formula. That's the probability of D and C happening divided by the probability of C happening. Well, we know the probability of C and D happening because we've just calculated that in part A. The order obviously doesn't matter. C and D is exactly the same as D and C. So we know that's 0.18. And then we need to divide by the probability of C happening, which we're told is 0.2. So if we work that out, we get 0.9. And in the last part, part C, we're asked to find the probability of C happening or D happening, so the union of those two events. Well, we're going to use the formula that tells us how to calculate a union. And you should know this formula from the previous example. It's the probability of C plus the probability of D, but minus the probability of C and D. And that's a useful formula to remember. So we can just substitute in what we know. The probability of C is 0.2. The probability of D is 0.6. And we need to subtract the probability of C and D, but we found that in part A, which is 0.18. And if we work out what that is, we get the answer 0.62.